the inaugural Queneau Distinguished Professorship Lecture to be given by Professor Lynd. Now, one of the privileges of being the dean here at the Thayer School is the opportunity to honor and recognize some of our most talented and distinguished faculty, and that, of course, is why we're here today. This lecture celebrates the appointment of Lynd to the Paul and Joan Queneau Professorship in Environmental Engineering Design. Now, those of you who know Professor Lynd know that he has had, in fact, a long and distinguished career here at the Thayer School. He has been with us, and I got ahead of myself here. Lee, when did you join the Thayer School faculty? 1987, right? So he's been here for more than 2 decades of contributions, particularly outstanding contributions to the development of sustainable biofuels through his work both in the research laboratory, his work in the classroom, and his work as an entrepreneur. He's not only a member of the Thayer School faculty, but he also serves as an adjunct professor of biological sciences here at Dartmouth College, professor extraordinary of microbiology at Stellenbosch University in South Africa, and he is, of course, co-founder, director, and chief scientific officer of the local company Mascoma Corporation, dedicated to making cellulosic bioethanol and biofuels a reality. Now, it's particularly fitting that we recognize Lee with appointment as the Paul and Joan Queneau Distinguished Professor in Environmental Engineering Design. Paul Queneau himself was a distinguished professor here at the Thayer School. During his tenure as a professor of engineering from 1971 to 1997, Paul headed 12 inventions and created this professorship in 1990 with the income derived from 12 of those inventions, augmented with a grant from INCO, for which Professor Queneau served as Vice President and Chief Technology Officer before coming to the Thayer School. The chair was designated to support a Thayer School faculty member working on engineering design and solving the difficult problems of environmental degradation which confront the world. The chair was to be known as the Paul and Joan Queneau Professorship in Environmental Engineering Design. Paul included his wife in the name of the chair because of her equal commitment to protecting the environment. And I think from what we all know of the work that Lee has accomplished over more than 2 decades, he is absolutely a fitting recipient of this honor. He's an expert on the use of plant biomass for energy production, and his contributions span science, technology, and policy domains, and include leading research on fundamental and applied aspects of microbial cellulose utilization. His research group has addressed these issues, as we said, for over 2 decades, authored over 75 archival journal publications, book chapters and reviews, 11 patents and patent applications. He's a frequent invited presenter on technical and strategic aspects of biomass energy, has 3 times testified before the United States Senate on issues in this area, and was a speaker at the 2007 Nobel Conference. In 2007, he was also the inaugural recipient of the Lemelson MIT Sustainability Prize for inventions and innovations that enhance economic opportunity and community well-being while protecting and restoring the natural environment. Professor Lynd holds a BS in biology from Bates College, an MS in bacteriology from the University of Wisconsin, and master's and doctoral degrees from right here at the Thayer School of Engineering at Dartmouth. Lee, Thayer School is pleased and honored to designate you as the Queneau Distinguished Professor of Environmental Engineering Design. Congratulations.
Can you hear me in the back row? Yes. No? Against advice, I think I'm going to do away with this. So it is a wonderful pleasure and honor. My goodness, I had no idea how many people would be here, and I didn't expect this many. So here's what I'm going to do. I'm going to start with some thanks. Seems like a good time to do that. Talk about some themes, talk about my journey. I'm not thinking of this journey as done, folks, but I'd like to give you a sense of how it looks from where I stand now and then offer some lessons. So in terms of, I'd like to start with my family. most notably and most particularly my wife Betsy, who has been with me through this entire journey, my parents, my children, the Rybecks, the members of my group, past and present, who have seen fit to contribute to this effort, and I sincerely hope have been able to take as well in ways of lasting value to them. I'd like to thank my deans, most particularly and recently Joe, but before Joe, Lewis and Elsa and Graham and Hutch. I'd like to the members of the Thayer and Dartmouth communities, my mentors. I don't think I've left anyone out, but if I have, I thank you too. And I do want to particularly, though, thank and acknowledge the Queneau family and Paul Queneau. I'm actually honored to be the second recipient of the Queneau Chair and to be following in the footsteps of my dear friend and mentor, Charles Wyman, who was the first holder of the Queneau Chair. And I was privileged to know Paul, who, as Joe says, truly was a distinguished inventor in his own right, and it's a great honor to have his name go forward with mine. Paul talked a lot about heavy industry, as those of you who knew him will remember, and had the, I think, quite correct notion that it is indeed the heavy industries making things we use a lot of, which are responsible for many of our environmental problems and challenges, and therefore also need to be parts of the solution. I want to tell you, though, a little story, though, about Paul before we get started, or my experience with Paul and Joan, in fact. So they actually lived about 2 miles from us in Meriden. And I believe it must have been just after I was, no, I guess I wasn't yet hired as a permanent faculty member. Anyway, Paul and Joan invited Betsy and me over, and it turned out that Millette Morgan and his wife were also there. And the funny thing was, you know, I kind of assumed that they knew me and they invited Betsy because she was coming along, but when we walked in there, I saw Joan sort of elbow Paul and say, "It's her." And it turned out that my wife Betsy had been Maria in The Sound of Music in the local community theater production, and they were actually a great deal more excited to have her in her living room than they were me, and that's fine. Okay, so with that, I want to start by reading you something. This is actually a book that an undergraduate, Sean Hogan, gave me, as near as I can remember, in about 1991. It's a great book, and it's actually been redone recently. It's called The Prize by Daniel Yergin, sort of the history of the world seen through the lens of oil. But I want to read to you a bit, and I do remind you, this is not written from the Dartmouth Alumni magazine, okay? So, the venture had its origins in a series of accidental glimpses, and in the determination of one man, George Bissell, who more than anyone else was responsible for the creation of the oil industry. With his long, towering face and broad forehead, Bissell conveyed an impression of intellectual force. Bissell had worked his way through Dartmouth College by teaching and writing articles. For a time after graduation, he was a professor of Latin and Greek, and then went to Washington, D.C. to work as a journalist. In his spare time, he studied to become a lawyer and taught himself several more languages. Altogether, he became fluent in French, Spanish, and Portuguese and could read and write Hebrew, Sanskrit, ancient and modern Greek, Latin, and German, a standard I certainly hope you won't hold me to. Ill health forced him to head back north in 1853, and passing through western Pennsylvania on his way home, he saw something of the primitive oil-gathering industry with its skimmings and oil-soaked rags. Soon after, while visiting his mother in Hanover, New Hampshire, he dropped in on his alma mater, Dartmouth College, where in a professor's office he spied a bottle containing a sample of this same Pennsylvania rock oil. It had been brought there a few weeks earlier by another Dartmouth graduate. Again, this is not the Dartmouth Alumni magazine. A physician practicing as a country doctor in western Pennsylvania. Bissell knew that the viscous black liquid was flammable. Seeing the rock oil sample at Dartmouth, he conceived in a flash that it could be used not only as a medicine, but as an illuminant, and that it might well assuage the woes of his pocketbook. That intuition would become his guiding principle and his faith, both of which would be sorely tested during the coming years as disappointment consistently overwhelmed hope. So, at one level, I don't remotely deserve the comparison, or perhaps which I implied by reading that. On the other hand, I think people seldom change the world without first believing they might. And I think the world needs some changes, and so I'm trying to proceed on the faith that it just could happen. Okay, so I want to start off with just a few themes that I will actually return back to at the end when I talk about the matter of lessons. I'm going to use this language of top-down and bottom-up in terms of some of the lessons I draw from my experience, which I'd like to share with you at the end. Simply put, bottom-up is kind of what most scientists do, and also what many engineers do when you're trying to understand something better, advanced technology. And then top-down is more evaluating and envisioning performance relative to success metrics. Yes, I know engineers do both of those. I'm not claiming to be unique. But just to give you a sense of how these play out in the biofuels domain, so you can do applied biology with the ultimate goal of getting faster and better catalysts, things that make reactions happen, and there's a bunch of topics there. You can also try to get better unit operations, as the chemical engineer would call them, and better processes altogether, better integrated components, so process engineering. There's the whole matter of resource efficacy, which is, it seems to me, coming at it from a pretty different perspective. And there's also the matter of economic efficacy, or if you will, making a business proposition of this. And somewhere in the middle, which you can either approach from a bottom-up or a top-down way, is this matter of where the heck is the raw material going to come from all of this. So don't want to go into that in detail. Some of those things will be illustrated. That's kind of the landscape for the discussion today. But what I really want you to take away and remember, please, is just this general and I hope rather intuitive notion of bottom-up, looking at the details, the technology, the science, and top-down, sort of how it fits in the world, if you will. Okay? So here's the second theme I want you to remember. There's only three. First one is bottom-up and top-down. Second one is thinking about ends and means. Seems to me, looking at this spatially, it makes a pretty good two-dimensional space. So what I'm thinking of is the ends and means of a career or an education that has a technical component. And so, for example, traditionally we think of disciplines along the means axis, maybe biological, chemical, environmental, materials and mechanical, computer, information, electrical, what have you. And then there's the things you want to bring that to bear on, okay? And I mentioned two here that are prominent at Thayer School, and anyone I think would say are important: health and sustainability. And I think it's fair to say that certainly within academia and many other walks of professional life, the standard way to go at this is to develop an expertise and kind of, work across applications over time. But fundamentally, you bring to bear computational fluid dynamics or molecular biology or whatever it is. But I'd like to think about now, or to lay out for you now, the notion that you can also actually organize a career around the end more than the means. And I think I'll convince you that, frankly, without entirely doing this by design, this is what I have ended up doing. So we literally do molecular biology, global resource assessment, two rather different scale activities, and I won't say everything in between, but a number of things in between. So idea number one, bottom up and top down. Theme number two, ends and means. Theme number three is this general idea of sustainability, but I'd like to approach this from the point of view of what do you need for a society to be doing well? And it seems to me that a pretty good list of cornerstones for the well-being of human society in no particular order are peace, prosperity, and sustainability. I notice if you don't have any one of those, you better watch out for the other two because they will be threatened. And furthermore, I would assert, I can talk about this at more length, but I would assert that all three of these are not just impacted, but dominated by resource access and utilization, and most particularly and increasingly by energy. And in fact, if you think about them for a minute, the definition of sustainability, at least in a material sense, people use the term more broadly, but the material sustainability is nothing more or less than the ability to can have continued access to resources without exhausting supply. Prosperity, when you really think about what does prosperity mean if it doesn't mean access to resources? Fundamentally, access to resources is it's more fundamental than money, I would submit, because it's really the basis of the wealth. And then finally, you know, what do people get into conflict for? Typically, resources, often put forward as something more ideological, but if you look at it in retrospect, resources are almost always there. This is not a new story. This has been true throughout human history, but a convergence of factors, which I'm not going to spend a long time cataloging, but I submit it is my view and my motivation that a convergence of factors makes this business of resource access and utilization particularly critical now, and indeed centuries from now, when people look back on the age that we all live in, I think the number one question they will ask is, it was obvious in the early part of our century, it was obvious that humanity needed to make a transition from our capital, our resource capital, to our resource income. And I think they will evaluate us in significant part based on how we did at that. So again, just to look at this in historical context, there have really only been two major resource transitions in all of human history. The first one was going from hunting and gathering to pre-industrial agriculture. The second one was going from pre-industrial agriculture to perhaps pre-sustainable industrial. That is the Industrial Revolution. And the third one is going from industrial to non-sustainable industrial to sustainable industrial. The third one hasn't happened yet. And indeed, I put a question mark, like when are we going to get started? And there's signs that it's starting. And it's interesting to think about the different things that most people did and the places we got energy and power in these different times. But what I really want to focus on is here. World population in around 2000 BC was about 50 million people. World population at 1750 at the start of the Industrial Revolution was about 750 million, and world population now is about 7 billion. A disturbing order of magnitude trend. Every time there's an order of magnitude more people, we have another resource transition. And the first one literally took thousands of years. The second one took hundreds, and by most estimates, we have less than a century to make this one. And not only that, but in the earlier, more disaggregated human society, there was a lot of opportunity for parallel experiments, parallel human experiments. And some of those worked and some of them didn't, and the ones that didn't work didn't hold back the ones that did. But today, in our integrated global world, that's a lot harder to do. So the scale of potential failure now is much larger. So basically, in this third transition, we have more people, less time, and the stakes are higher. And so this is briefly why I think this is the defining challenge of our time. One more comment on this theme, and then we'll move to the next stage. So our circumstances are changing radically. In the past, we've had relatively few constraints, low prices, and we've been living off of our resource capital. In the future, we will have many more resource constraints, I'm sure of it. We will have higher prices in general, and we will need to learn to live off of our resource income. And I comment that big systemic challenges require big systemic solutions. In my view, simply put, viable paths to a sustainable world for all resources and all sectors almost never feature single isolated changes. They almost never feature new supply without increased resource utilization efficiency. And they almost always feature multiple large, complementary, and I would add currently improbable changes. I think we need to get comfortable with the improbable, with embracing it, with learning how to analyze it, which is counterintuitive for engineers to do. The classic method is if you take a multivariable problem, say a sequential problem, and each one has got a probability distribution, you sort of go for the center and maybe do a sensitivity analysis. But you know what? That approach doesn't lead to a sustainable world. Currently, probable trends are not sustainable. Therefore, we have to look beyond those trends to find sustainable futures. And interestingly, business as usual is a term of art in scenario planning, but it's got a strong implication, i.e. that we can keep doing what we're doing now. But if, like me, you believe that's wrong, then business as usual is not a baseline, it's a fantasy, and that's a rather different interpretation. And a major motivating factor for me is that, so, okay, we need to get good at confronting the improbable. It seems to, and changing the improbable, putting it into the probable column, it seems to me the very first step to confronting the improbable is to show that that alternatives are indeed possible. Then you can move. Until you do that, it's hard to get a discussion going. So I want to say a little bit, you've all been kind enough to come and listen, and I realize many of you have heard pieces of this story before, so I wanted to try to figure out a way to tell it that was different from how I told it before. And so I'm going to put this in rather personal terms for a little while. I'm going to think about the journey. And I'm going to think about this in 3 dimensions. The bottom up, the top down. I might have put the top on top of the bottom, I thought later, but oh well. I'll also talk about some comments about professional trajectory. And just to give a sense of my initial condition in all this, I grew up with absolutely no idea I would ever be an engineer, or nor any particularly great interest in that. I was much more interested in being a naturalist. In fact, at one point, my room was organized as a forest ranger's office when I was about, I don't know, 8 or something like that. I also come from a service-oriented family that at least my parents' example is very much, you know, how can you go out and make the world a better place? That wasn't required or demanded of me, but I do feel pulled in that direction. And so I was working on an organic farm in 1977 in North Reading, Massachusetts, and I was really impressed with the heat. Incorrect. The temperature, that's what I observed was the temperature. I was really impressed with the temperature that thing developed, about 150 degrees centigrade. Excuse me, I'm getting lots of problems. 150 degrees Fahrenheit. I really do know what I'm talking about, believe me. And I came up with what, with retrospect, is an absolutely cockamamie idea. You know, you keep in mind, 1977, you know, big energy. I was a biology major, maybe that's my excuse. I hadn't thought a lot about this sort of thing, but I thought, wow, I need to do my senior thesis on something. Maybe I'll do it on compost as a heating source. Now, at this point, I would say, you only can get the heating value out of that, so you'll never get more than what you're burning, and what's really going on is that it's losing heat slowly, and therefore it gets hot in this sort of self-accelerating process, but you don't have any energy more than what you put in the heat, and the real limits to that idea, to say the least. Nevertheless, that's how I got started. And then in 1978, I was junior year abroad in Scotland, and I actually saw a photograph, and I'll show you one of these, of colonies of microorganisms dissolving cellulose. And I even learned that they grew in the absence of oxygen and they made ethanol, which I kind of knew might be a fuel. And so that made an impression on me. That same year, I was sitting in a seminar of a bunch of experts at the University of Aberdeen. I was a junior in college. And one of them made the statement, you know, if this carbon is a problem, then fuels from plants really don't make any sense because these fuels are more oxidized than hydrocarbons. Therefore, the CO2 per unit energy released or per mile driven is going to be higher on biofuels. And we better, you know, anyone who's attached to biofuels, which I wasn't really then, frankly, I was still in the compost heap phase. Anyone who's attached to biofuels had better hope there isn't a carbon problem. And I thought to myself, now I was a biology major now, I don't think that's right. Where does that stuff come from? Plants. Where do the plants come from? CO2. So you actually have to remove CO2 before you can make a biofuel, and if you then burn the biofuel, you can return the CO2. Was I brave enough to raise my hand? No, actually I wasn't. But nevertheless, there was this notion of this carbon cycle, which I did have some involvement with going on forward, as you'll see. I did my undergraduate thesis on, of all things, I'm kind of Johnny One Note, ethanol from biomass using thermophilic bacteria. And part of that thesis was a mass action hypothesis that took me about, I'm not going to go into the details of that, but it's not that complicated actually, but it took me about 12 years to test, and indeed the test was negative, as you'll see. But there's more than a few, more than bumps in the road. As I left my undergraduate biology education, I knew that I wanted to impact energy and environment. What I didn't know was how. And I also saw at that point, some things correctly, some not, and I'll try to fill you in on some of the things I learned, but I assumed that one had to choose between what I've called in this discussion bottom-up and top-down approaches. Because after all, they're completely different. Why would you presume that you could do both of these? And I chose very consciously bottom up. I thought, you know, I want to put my effort into generating new alternatives for the world, not sort of comparing and analyzing and advocating for alternatives other people generate. That's important, but it's not what I'm going to do. Didn't turn out that way entirely. I entered graduate work in bacteriology, and I was very motivated to work on cellulosic biofuels, of all things. And my advisor, who was one of the most active people in the field, said, sorry, but I don't have a project for you in that. I kind of thought it might have been nice if he told me that in advance. And he pretty much said, but look, I think you're going to like this one, and it actually might have more energy impact anyway, so it's responsive to that. Well, I didn't have much choice, and I said, okay. By the way, that same year, Diane Knappert, Hans Grethlein, and Al Converse in this building it literally invented the modern biomass pretreatment field, and that was actually reasonably good timing with my, at that point, parallel path, because it was one of the things that happened before I came here. I did a master's thesis on carbon monoxide utilizing microbes, and I call this a gut check. I was invited to continue to get a PhD in bacteriology, but you know, I was really interested in applications. And I felt like nobody who I was talking to in the biology environment had any idea where the steep slopes of increased capability for increased understanding lay, i.e. what mattered in an applied sense. They were on a curiosity-driven path. They would write and look, these are friends of mine, although it may not sound like I'm talking about them that way, but the fact of the matter is, and I would say, I have said this to them, they had a standard opening grant proposal, grant paragraph in their grant proposals about how they were going to solve the world's sustainability problems, and after that it was all curiosity-driven science. I have no problem with curiosity-driven science, but I don't think it's the same thing as, nor is it all that productive a way, although occasionally serendipity happens. I don't think it's the same thing as solving the world's problems. Now, a couple of other things here. Some of you know Ed Lightfoot, one of them, or know of him, one of the most famous chemical and distinguished chemical engineers in the United States. He was the Lightfoot of Bird, Stewart, and Lightfoot, which is now in its like 35th edition or something like that. Very outspoken senior guy. He was my mentor as I began to think about making a transition to engineering. And I remember Ed Lightfoot looking over the top of his split glasses and saying to me, Lee, let me make myself perfectly clear. If you go to Dartmouth to study engineering, you will be walking off the edge of the earth. Furthermore, when I spoke to, look, here was the gig. I went out to Madison, Wisconsin, chose it from all places in the world. My wife, Betsy, and didn't find my fulfillment there. So it kind of seemed like it would be appropriate to let her choose our next place. So she chose New England and actually had a program in Keene, New Hampshire, which served her very well. So I was kind of looking in radii around Keene, New Hampshire. And that fell on Dartmouth before too long. It's about an hour away. And also fell on UMass and a few other places. And most places I wrote said, well, you know, you could get another bachelor's degree if you really wanted to. And I was kind of like, you know, I kind of thought, look, if bacteriology wasn't applied enough, maybe I should try engineering. I'm not sure I could do it. And Dartmouth said, well, I met with Al, and he said, well, why don't you come, you know, be a graduate student here? And I said, could I do that? And he said, well, yeah, you'd have some courses to make up, but we'd be interested in what you'd bring to the table. And the other part about that, so interestingly, and I'll have to speed this story up soon, but this may be the most important part in some ways. So I ended up in Hans Grethlein's office. Hans and Al worked closely together on biomass, and I was sort of champing at the bit. My wife's program had already begun, and I didn't know what I was going to do next, and so I went in, I was all excited, and told Hans I was interested in cellulosic biofuels. And he said, I'm not sure we have a project for you in that. And then the phone rang. I'm not kidding. Then the phone rang. And I remember looking at the ceiling thinking, you know what? It's not going to take me 2 years to hear no this time. And he got off the phone and he said, now where were we? And I said, you were saying that you didn't have a project for me in cellulosic biofuels. And he said, yeah. He said, you know, we're kind of thinking maybe we'd go on to the next thing, and the money's not that solid and all the rest of it. And I said, I think I might have a few ideas you haven't thought of. I mean, I had a lot at stake here. I've been through this once before, okay? And he looked at me kind of, I know those of you who know Hans, he kind of looked at me like this. He said, well, I guess that's the way innovation happens. People not taking no for an answer. And I've been really grateful for that response for a long time. Okay, moving forward. I did an MS thesis in energy efficient distillation. I figured, you know, that's what the people said was the problem with the stuff I wanted to do. Man, you'll spend an arm and a leg to use the energy for this. I said, fine. I came to do what was important. I don't know what's important. I'm listening to you, and that's great. And we got 3 patents and a couple of papers, and I concluded actually after that distillation was not a key constraint. And for the second time was invited to continue towards a PhD, but didn't in that direction, because I said, look, I came to solve things, and I don't think this is a problem. And so it was back to biology. We actually did, in the course of my PhD thesis, the first example of thermophilic bacteria converting pre-treated substrates which were made with that process that was invented here before I came. But when I came time to write up my doctoral thesis, I made a calculated gamble. The calculated gamble was that I thought I probably had enough data to satisfy my committee, and I was kind of up for sort of a big, you know, let's do something intellectually challenging here. Had enough data to satisfy my committee from my experimental work. So actually, if you go look in the library at my thesis, about half the pages are actually top down rather than bottom up. At least they're not based on experimental science. They're based on energy balance, resource availability, environment, economics, stuff like that. And I had an added reason, because if you think about it, the oil prices crashed in about 1985. People were leaving this field in droves and, in fact, shooting the boat when they left it so that no one else could sail in it. I'm not kidding. And I had people come up to me, and I think I've got this later on, say, well, you seem bright enough. Why are you in this dead field? I mean, what's wrong with you? And so I felt like, by the way, I did my Doctor of Engineering thesis on the same subject that I did my bachelor's thesis. I felt like I actually had a lot of stake in asking these questions with integrity and, frankly, being willing to hear the answer if these people were right and it really was stupid. What I concluded at that time was it was very hard to get money in, and therefore people were finding reasons to justify their leaving, but there was nothing fundamentally wrong with the idea. So I kind of recommitted. I said, yeah, this is what I want to do. I set out to try to make a difference. The world still needs renewable energy. This is something I'm positioned to have an impact in. I don't believe those critics are right. I'm going to go for it. By the way, in 1991, we tested that mass action hypothesis, and it was wrong. In any case, we published a paper. I was the lead author in a paper in Science in 1991, and it wasn't even an experimental paper. It was sort of a strategic, I think the title was Fuel Ethanol from Cellulosic Biomass, of all things. And we were among the first to show the zero net carbon potential of biofuels. Not necessarily the first, but it's fair to say among the first. Recall that realization 14 years earlier when I was sitting in that lecture and said, that's not right. So eventually Science published it. And my understanding is that when a certain board, I don't remember which one, I'm not sure I ever knew, at the then Solar Energy Research Institute saw that figure, that they all got up and danced around the table. So at least it was a new realization. Okay, moving forward, I did a lot of work for the next decade in sort of fermentation studies, kinetics and reactor design, some pretreatment work. In 1992 or so, I tested waste paper sludge from the Berlin Gorham plant, which has changed names 4 times and then shut down since then, but is part of the story. Began trying to genetically engineer thermophilic bacteria with a brave biology student, Taryn Claypatch. I stopped in about 92 working on anaerobic digestion, which was a valid thing to do, but it's the one thing I was doing other than biofuels, and from then on it's been all biofuels. So in 1991, actually, someone approached me after that Science paper came out and said, let's start a company. I said, great, I'm all about world impact, sounds good to me. Spent a lot of time on that, 4 years. It was called Independence Biofuel. I still kind of like that name. And was never funded. Interesting story, but don't have time for all the stories. I was on, although I'm making a pretty good go at it, right? I was on something called, we called it colloquially the Car Talk Committee, because the full name would take too large a fraction of the remaining talk. But essentially, it was a committee to the executive office of President Clinton, which didn't mean we sat around for beers with him. And the goal of this was to recommend policies that would reduce greenhouse gas emissions from personal vehicles to 1990 levels in 3 different time frames, and I was the biofuels industry representative. This was my first experience seeing policy formulation and evaluation and negotiation up close, and quite a school it was. We met 2 or 3 days a month for a whole year, and some people were working on it full-time in between. So somewhere around there, Dan Lynch, Professor Dan Lynch from the Thayer School, was teaching a course in sustainability, and we had a guest, and we went out to dinner, and I was sitting next to him, and he looked at me and said, why are you advocating for this idea of making biofuels out of stuff you grow when the world's going to have trouble feeding itself anyway? He said, don't take this personally, but I think this is going to be more of a problem than a solution from an environmental point of view. And that's one of a few good hard questions, and you'll see, not only because of Dan's impetus, but that was a key point. A diagram I still use in most of my seminars, although it ended up on the cutting room floor for this one. Believe it or not, I left something out. A diagram I used for most of these seminars was actually something, right after Dan said that, I went back to my office and I drew up this diagram about basically why you pretty much had to have biofuels. A little more on that later. So I proposed this term, consolidated bioprocessing, in an article in 1995, and with my friend Charlie Wyman, we did the first economic analysis of it, which basically said, if you could make this work, it would be a slam dunk. I spent 2 intensive, right about when I got done with my unsuccessful efforts trying to start that company, okay, literally in the same plane ride as I got on the plane all excited about the company, I thought about it and thought, you know, Lee, you've got to be honest with yourself. This isn't going anywhere. And by the time I got off the plane, I said, fine, the world needs a big research center to really do what ought to be done in biofuels. I'm in. So I worked with a guy named Bruce Dale from Michigan State University. Elsa Garmeyer was very supportive, dean at the time. And I'm telling you, I was absolutely certain this was going to get funded. And we got, not only did we not get funded, and keep in mind, this is like about a 3 out of 120 success rate in this program. So, you know, being brave was never my problem, although I had some invitation to be otherwise. We didn't even make it out of the box. At the first opportunity, we could talk about why. In 1998, I went to Stellenbosch, South Africa, to meet experts in yeast cellulase expression. Those people I met during my 36-hour visit are still dear friends. My family's been there. I think I've been there 10 times since then. And you'll see that yeast cellulase expression plays a very large role in Mascoma's picture. But maybe one of the important parts of this story to understand is that the 90s were something of a downward spiral for me, frankly, professionally. I was good at seeing dots on the horizon. You may sense that in my personality. I was not so good at showing steady incremental progress towards them. And you can just imagine, you write your first grant proposal as a newly minted academic, and they go, well, he can't have a track record, might as well take a chance on him, and you get some money. And then you come back and you still are telling the Brave New World story, but yeah, but how, you know, at a certain point it's like, what have you done and what are you going to do? And I was not so good at that. Not only that, I was not extending fundamental frontiers. And I've always been motivated to make a big impact, but one of the things I've learned is it's really hard to make a big leap forward in applications without understanding something new, all right? And so I frankly, in retrospect, I don't think I was paying enough attention to how things worked. Maybe it was a healthy instinct to be impatient, but it wasn't actually serving me well, okay? Money was really scarce. I wrote to one sponsor 6 annual solicitations, 6 years in a row, turned down 6 times. And when I left for sabbatical in 2001, slightly off this scale, but you get the idea, I left 3 people in the lab, not a big lab, and I was really wondering if whether the effort to do top-down and bottom-up was a mistake, actually. Keep in mind, I'd spent 4 years on that company, and I'd spent 2 years on that engineering research center. That's a good fraction of a decade, and except for all of the edifications, didn't have much to show for it. Well, things started to change, fortunately, and both of these were major factors. I spent a sabbatical at the University of Stellenbosch. I more or less said to myself, you know what, I don't think people are taking this story seriously. I don't think they're taking me seriously. as a fundamental scientist. What can I, a scientist who knows their fundamentals, whatever my motivations might be. And I thought, so what can I do about that? And I thought, you know what? I'm going to write a review like they've never seen. And here it is, 786 references. This is one of the 3 or 4 most cited reviews in molecular and microbiological reviews, which is one of the most prestigious places you can put this sort of thing. So through a large effort with a lot of other people, 3 other people who worked very closely with me, we actually succeeded at that. And frankly, at this point, I think it's very fair to say our group is perceived as a world expert in microbial cellulose utilization, the fundamentals, and that certainly wasn't true then. That review played a big part of that. I wouldn't be standing before you today doing any of these, or most of these interesting things, were it not for the fact that Lewis Duncan, the dean at the time, came up with some rather large NIST funding, which it was like rain on the desert, as if I'd been planting these seeds, waiting at some point in the future. Maybe when I wasn't there, I didn't know. But when the rain came, a lot of these things sprouted, and in fact, met or exceeded my hopes. And finally, my dear aunt, my mother's sister, Cushing Dolbear, I'd been trying this sort of big picture stuff and top-down stuff, and again, I'm not sure I was getting that far. And I was in Washington, D.C. for something on a Thursday, and I managed to get an appointment to talk to the DOE on a Friday about something I didn't think had much chance of happening. I had in mind this sort of big, comprehensive analysis, strategic analysis, because, with biofuels, it's not enough to just do the science. People sort of want to make sure it makes sense. So, and funding was lousy. I thought, well, if I'm going to turn this around, I guess I got to be able to talk about that, and I already had an interest in it. But I expressed at breakfast that morning, I said, Cushing, I'm just not sure anything I'm going to do is going to make a difference, or even if it makes sense. And she was an internal optimist, and she had a lot of experience with uphill slopes herself. And she said, Lee, what I found in my life is that you just go around and you keep knocking on doors, and sometimes at the most unexpected places, they just open and you walk through. Well, darned if I didn't go to the DOE that morning talking about, in fact, I kind of felt I wouldn't even pitch my idea. I'll just see these people. And one of them said, so what about that big analysis idea you were talking about last spring? And that turned into the role of biomass in America's Energy Future Project, which was funded by the DOE, the National Commission on Energy Policy, and the Energy Foundation. It was and is the largest analysis of mature biomass conversion technology. It was also co-led with Nathaniel Green, had 11 institutions, co-led by Nathaniel Green of the Natural Resources Defense Council, and this is a very new dialogue of technology people talking to environmental advocates. Quite a few technical advances, including 3 papers in the Proceedings of the National Academy of Science. Boy, I remember when that first one got published, I kind of thought, gee, I never thought I'd be here. John's question. Okay, so money started to get a little less tight. And there I was driving with 2 graduate students down to a one-day deal to do some policy stuff in Washington, D.C. They were interested, and I figured, look, bring them along. And so we're taking the 6:05 flight, U.S. Air, down to Washington, D.C. from Manchester, and it was something like 5. And John said, Lee, how many courses do you have in economics? None, actually. And how many courses do you have in public policy? I said, none. And government? And he said, don't take this wrong, but why does anyone listen to you on this stuff? And I think I've learned, kind of like Dan's question, that there's often some value there in these hard questions. And so I didn't have an answer, and he couldn't see that my face was red, but after a little while I said, I think I do have an answer, actually. And I said, I've done enough work in policy domains to know or have some understanding of what policy people really do. And what they really do is they have models of the world, conceptual or analytical, and they kind of say, well, if this policy were different, what would the world do? How would it react? How would it impact natural systems, things of that kind? I said, you know what, I don't do that. Partly because most of those things are probabilistic exercises, and I don't need a big model to tell me that we need to do things differently. I said, my contribution to these policy exercises, every policy exercise I've ever seen, has been underinformed by a sense of the possible. And my contribution is, in these policy exercises, invariably, is to illuminate the possible. And that actually is a technical thing that you don't really need courses in government or economics or whatnot. In 2006, Mascoma Corporation was co-founded. After a 2.5-hour discussion, Vinod Khosla, one of the world's 50 richest people, co-founder of Sun Microsystems, said, let's do this. It wasn't quite that simple, but nevertheless. Earlier this year, there was a special volume that published the results of the role of biomass in America's energy future, and we launched the Global Sustainable Bioenergy Project. So, just some pictures. So this is, you see those little dots in the middle of those clear zones? Those are colonies of cellulolytic bacteria, like the ones I saw, not the actual one, but like the ones I saw in 1978. Come on now. Thinking. Okay, whoops. Oh, come on, that's giving it all away. Well, I'll talk about that one. That was the figure that oh my goodness. At a certain point, you just have to stop and let it do its thing, right? Okay, there. So I'm not going to read that stuff to you, but those are things I said in my thesis in 1979. This is a diagram, pre-PowerPoint, an early version of consolidated bioprocessing. It happens to be my wife's hand, then girlfriend. So this has been a family affair for a long time. Here I am looking just like I do today, although I did manage to keep most of my hair. In any case, with Hans Grethlein and Rich Wolken down in the basement. Here's the figure from Science that had the circular carbon flow I mentioned. There's, I still like that logo, but in any case, there's a page from the cover page of a business plan for Independence Biofuel. There's a lot of small print, but somewhere in there you see $12 million for 5 years, which was our ERC cover page. So I don't have much time left, and so what I'm really going to do, think of this as follows. I once actually had an opportunity to ride an airplane over a part of Botswana that had a lot of wildlife, okay? And what I came to appreciate is, you know, it's great to be there in the weeds with the binoculars and looking at the spots on the giraffe, you know, wonderful thing. But it's also cool to kind of fly over and see the herds of them and all. So we're going to do a flyover, okay? So biomass energy, we tend to buy energy in different units, but you can put them on common units. And there's some interesting things that can be observed. You can also put forms of biomass on common units, and you find that cellulosic biomass is one of the cheapest sources of energy out there. Coal is somewhat cheaper, although if you have to pay for carbon, that isn't true. But at $4 a gigajoule or so, the purchase price of cellulosic biomass is competitive with oil at $23 a barrel. There are a great number of criteria and a great number of forms of biomass. In the interest of time, let me point out the conclusion I draw from this. If you look at the cellulosic column over there, the real rub with cellulosic, it scores well on a lot of things, which some of the other forms don't score so well on, except for processing costs. It costs too much to convert this stuff. And that's because cellulosic biomass is recalcitrant, because plants have been outrunning fungi and microorganisms that have been chasing them for 1.5 billion years. Here's some forms of cellulosic biomass, wood chips. This is miscanthus, which is 1 year old. Emily Heaton in the picture actually growing it on her father's farm in Illinois. Waste bagasse, paper sludge up from the Berlin mill. So, well, fine, maybe there's some reasons to do this, but what's stopping us? And if you think of cellulosic biomass as going to something reactive and something reactive going to fuels, essentially it's the first part that is the rub. It's costly, it has the greatest potential for R&D driven reductions, and frankly, if you can make that work, you're in. You don't have to, the rest of it's pretty well known and pretty cheap. So improved fuels and fuel production, although many companies and others have targeted it, in my opinion, you could make ultimate advances there, and you're still stuck with your source of raw material, which is where the main limitations are. So we would have a cellulosic biofuels industry today were it not for this recalcitrance. The thing I've been working on since 1978 is this idea of having microorganisms that in one integrated step can do all of the 4 different biologically mediated events you need to do to take plant matter and make ethanol, or for that matter, any other fuel. We call this consolidated bioprocessing. In a recent roadmap that led to the formation of 3 gigantic centers, DOE USDA roadmap, it was written that CBP is widely considered to be the ultimate low-cost configuration for cellulose hydrolysis and fermentation. So to get there, if nature gave us, fundamentally, we need microbes that can use cellulosic biomass and can make fuel well. What we have is microbes that can do either one of those, but not both. So you can either start with microbes that make fuels well or microbes that utilize cellulosic biomass well and work towards the middle. It helps if you know something about what's going on. So there is this fundamental issue. And Mascoma, building, I think it's fair to say, on many of my contacts, although not all of them, has put together a team of people from around the world to try to address all of these. The Bioenergy Science Center, which I think was somewhere in that chronology, I may have missed it, but that's unbelievable to me. In 2007, after all those years of walking through the desert, the DOE established 3 $125 million 5-year research centers on biofuels, and I proposed the theme of one of the ones that won, and am a vice president, and that's very satisfying. The University of Stellenbosch, over here on the yeast, also VTT in Finland. And so this is from that review, the one I mentioned that I figured I had to gain some credibility in fundamental circles. We proposed this idea of alternative paradigms, and this is interestingly both a scientific paradigm and a technological paradigm. The world had been thinking about biological conversion of cellulosic biomass in a mode where you make your enzymes and then you add them and the enzymes do their thing. And in this review, in the end, we sort of developed the idea that, you know, it actually is more different than it might first appear, not only technologically, but fundamentally, to think about doing this with microorganisms. So we wrote in that review that the microbial paradigm naturally leads to an emphasis on different fundamental issues, organisms, cellulase synthesis systems, and applied milestones as compared to the enzymatic paradigm. So the enzymatic and microbial have different features, but in particular. So if you ask the question, what fundamentals do you need to think about if you're trying to understand this at a microbial level that are above and beyond the fundamentals you have to think about if you're trying to understand this at an enzymatic level? And the answer is a whole bunch. And I'm not going to go into those here, but the point is, and we weren't, actually I didn't put that list together till about a year ago. I kind of knew it was there, and I thought, wow. And so this is sort of a cartoon, an actual photograph of the enzymatic paradigm, where the biocatalysts are sort of, especially the cells, are off somewhere. This is actually the way nature does it. The microorganisms adhere to the cellulose, and those of you who think about boundary layers and mass transport and stuff like that can appreciate that those are two pretty different geometric arrangements. So, you know, the easy part is doing the economic analysis, saying that this, you know, could be powerful if it worked. There was a lot of pushback from biologists saying, this isn't going to work. It's got a fundamental problem, and the fundamental problem is that fermentation is so efficient that, and this is a good thing in a way, that most of the energy that starts out in the carbohydrate is still in the fermentation product, like 95%. Does that leave enough energy to make the cellulase enzymes? For those of you who, ATP is the biological energy currency. It takes 3 ATPs per peptide bond. Proteins are strings of amino acids joined by peptide bonds. So the basic criticism was, you know what, you've got a Volkswagen budget and a Ferrari appetite, and this is just not on, okay? And so we looked at this very systematically. This was this first paper in the Proceedings of the National Academy of Science. We found that there are mechanisms of ATP synthesis that are specific to growth on cellulose. In essence, nature had already figured this out. We just didn't know how. And so that removed probably the single biggest conceptual criticism of this notion. We've engineered microorganisms that grow naturally from hot springs. We've taken their biochemistry and sort of put fingers in the dike of the flow towards the products we didn't want, routing it all towards ethanol. This was done by Joe Shaw, a graduate student here. This is mixed sugar utilization, which that microbe does pretty well. I remind you, a flyover. So Mascoma's made some wonderful progress, both with thermophilic bacteria and with yeast. They achieved a 3,000-fold increase in yeast cellulase expression. Recall that trip in 1998 to Stellenbosch to talk to experts on this. And here's actually paper sludge being converted to yeast, converted to ethanol, by recombinant cellulase-producing yeast with no added enzyme, a proof of concept of consolidated bioprocessing. And I would acknowledge Vineet Rajgaria, who led the team at Mascoma. Let me be very clear, this is work that didn't happen in my lab. I didn't inspire directly, but I do feel some parenting rights on, if you will. The world kind of thought of this as a long-term prospect and dealt it rather with it skeptically. Interestingly, in March of this year, Helena Chum, a noted expert in the field, referred to CBP as a golden dream. And a month later, an expert, Bruce Dale, said many had thought that CBP was years or even decades away, but the future just arrived. Mascoma has permanently changed the biofuels landscape. And so, whoops, there's a picture of the nice Mascoma building, not very good detail, but there's our pilot plant in Rome, New York. That's outside the Rome, New York plant. We do classic economics. This is projecting, just again, flyover. This is projecting the economics as a function of oil price, the return on investment for mature technology. I could get investment much more easily if I could go out and do this right now, but it's also important to know where it's going. And, you know, different families of conversion processes, which this is chasing energy around, and this is more classical chemical engineering stuff. This is chasing energy around a projected mature process for biofuel production. I'm not going to go through every detail, but if you start off with 100 units of energy in cellulosic biomass, you've got about half of that as the ethanol, but you've still got most of it in chemical bond form. Recall that fermentation is actually very efficient at preserving chemical bond energy. And although biological and thermochemical processing have been regarded and still are as competitors, they're actually wonderfully complementary because the thermochemical processes are exothermic. They release heat. And the biological process is actually also exothermic, but the processing, and in particular distillation, needs a lot of rather low-level heat. And when you put these together, you get efficiencies that are just not possible from doing either one alone. And so you have a ratio of energy out to energy in this case, of about 10 to 1. So a little bit about the top-down perspective in the flyover mode. This is my favorite phrase about engineering. And it was written by a very distinguished chemical engineer from Berkeley. If engineering is the application of science for human benefit, the good thing I noticed that my watch is running faster than that, and you're all watching that. Okay, got the point? If engineering is, so since I'm watching this one, it wasn't so bad. If engineering is the application of science for human benefit, then the engineer must be a student of not only the application of science, but of human benefit as well. And in the interest of making some points near the end of this crisply and not keeping you too long, maybe I've already done that. I was hoping you wouldn't laugh uproariously at that idea. Let me just go to this, and we are looking at, just in a narrative way, what I believe to be true, and I was going to show you a little bit to try to flesh this out, but I used too much time telling the other stuff. What I believe to be true is that it is physically possible for the world to produce all of its transportation fuel from within currently managed lands without compromising food production and without in fact, with benefiting environmental quality. That's a mouthful. That's not organizing the system the way it is now. That is featuring multiple complementary, large, and probably currently improbable changes, as I mentioned earlier. But then again, that's the only prospect we have for making this work, so I don't apologize for that. So what I want to end on, and I've only got 3 more slides, so we're near the end. Thank you for your patience. What I want to end on is this project that we've initiated called the Global Sustainable Bioenergy Project. We have an international organizing committee. We issued a joint statement on issues in science and technology. We have a website. And the key hypothesis here is sort of asking as a question, is it, or the hypothesis is a statement, it is physically possible, we need to prove that to people's satisfaction, for bioenergy to meet a substantial fraction of future demand for energy services, e.g. at least a quarter of global mobility, while feeding the world and protecting the environment. In stage 1, we're going to have meetings in every continent. I'm doing a sabbatical and a leave term the beginning of 2010 to work on this. We're going to have meetings in every continent except Antarctica, where biomass isn't really much happening. And we're going to gather input on framing the second and third sections. We're going to have continental and common resolutions, somewhat reminiscent of the Continental Congress, and we're going to try to recruit participants and funds. In stage 2, we're going to address that working hypothesis. In stage 3, we're going to address implementation paths, including policy, economics, equity, etc. And so here are all but the last meeting is scheduled, and it's been very gratifying because the funding for these meetings has come from each continent to fund their own meeting. And so that's exciting. The first one is in the Netherlands, then Africa, South America, North America, and Asia. So let me close with some of the lessons I draw from my experience. And this is the part where that early discussion really was the important one. From a personal point of view, the things that have served me well have been clarity and perseverance. I'm not going to elaborate. Setbacks will happen, and boy did they to me. But I'm telling you, I've almost gotten to the point, it's not that I wish for setbacks, but when they happen, treat them as opportunities. Because over and over and over, the way I respond to today's setbacks is what lays the groundwork for future successes, and I'm quite convinced that if one responds badly to setbacks, you decrease the chance of future successes. Returning to the bottom-up and top-down, I assumed that it was necessary to choose between top-down and bottom-up spheres, but my experience suggests otherwise. Policy formulation and analysis, as I mentioned, is commonly underinformed by an understanding of what is possible. Illuminating the possible is a technical activity and does not require training in policy, economics, or government. I'm not saying it wouldn't be useful, but it doesn't require it. There is a seat at the policy table in my direct experience for technically trained people interested in big picture issues, but seldom a seat at the technical table for those trained in policy. In terms of ends and means, ends, for example, health, sustainability, sustainable biofuels, and medicines, by the way, figured this out a long time ago, not so common in some other areas, are a viable alternative means as an organizing principle for an education or indeed a career. So again, I do a lot of microbiology, I do a lot of chemical engineering, I do a lot of environmental science, those don't seem to make any sense, but they're all strung along something that has the axis of impact, need, service, whatever you want to call it. It's interesting when you start thinking about some of these things, not that you need to educate people at Thayer School in my mold, but at least it's informative as to some of the constraints and opportunities and necessities and lack thereof. And finally, I'm very grateful. Thayer School provided a fertile environment. I've had offers to go to places all over the world and work, and I stay here, thank you, has provided a fertile environment in which I've been able to craft a career organized in terms of ends as a more primary factor than means, and combining both bottom-up and top-down approaches. Thank you very much.
We're a little short on time, so we have time for just a few quick questions, and I'm sure Lee would be happy to entertain questions to follow at the reception, which is immediately afterwards. Yes, up here in the back.
Dr. Lynd, we've spoken before in the past, and you're probably aware of this, but the ideal, if you had a choice between the more ideal fuels that you could develop, I think you even mentioned butanol would be preferred to ethanol. And recently I received some information that said that the bioengineered E. coli, I believe it's Caltech, they have come up with a process to convert cellulose to butanol. And they're continuing on that site. You want to comment on that?
Sure. It was UCLA, it was Jim Lau, and all he knows how to do so far is glucose to butanol, but nevertheless, it's a good idea. I just saw him yesterday, so it's kind of funny. Look, go back to that diagram where you start with cellulosic biomass, go to an intermediate, and go to the fuels. In my opinion, the big challenge is figuring out how we can economically access something that makes sense to grow on the scale that fuel production demands. which means not corn, not soybeans, etc. Frankly, whether you go to ethanol or whether you go to a different molecule from a technical point of view, once you've got that platform, will work out. I will say, though, that the enthusiasm over fuels other than ethanol that can be made biologically is fed by two things. One of them is a policy problem, or a problem policy has created. The so-called blend wall, that we've got legislation based on 10% ethanol, and we've got vehicles guaranteed for 10% ethanol, and corn ethanol filled all of that up. That's not really a technical problem. Brazil uses much higher ethanol concentrations. The vehicles do fine. The other one is, frankly, the enthusiasm of people who want to apply their genetically engineered tools and don't really want to worry about cellulose and try to create a need. In the long run, I'm very confident, and I'm not saying this means that it will only be ethanol, but in the long run, price and performance will rule. We're not going to get fuels that don't compete on price and performance, out-competing fuels that do better. And they choose ethanol to run in Indy cars, so it does pretty well when it comes to performance. Yeah.
You made a comment that there's not managed land to also.
Yep. Well, I'm differentiating between wild land that first of all is a wildlife habitat, although there's some of that in managed lands too. But there are certain places in the world we would like to leave wild, and one of the environmental advocacy community's biggest concerns is the tendency to clear wild lands in ways that release a lot of carbon. There's vastly more carbon in the biosphere and in soils than there is in the atmosphere. So what you do with the biofuels and soils has a lot to do with what happens in the atmosphere. Okay? So I'm basically saying, fine, leave all the wild places alone. We're only going to deal with places essentially now that we use for forestry, for it's been a long day. Only places that we use for food production, for grazing, or for forestry. So within that land base, without sacrificing the food output of that, I believe that we could provide for the world's mobility consumption, although it would be a world configured differently than it is now.
Thank you all for being an attentive audience. We have a reception video.